My name is Emily Roll. I'm a mechanical engineer with a background in energy efficiency for both commercial and residential buildings. I am very familiar with energy codes and have used this knowledge to consult on hundreds of buildings and to develop incentive programs. I also have experience in energy modeling and calculating energy savings in commercial buildings.
And I am Tianyao Zhang. I am also a mechanical engineer with extensive experience in commercial building energy efficiency. I have conducted thousands of energy models and analyses to support utility programs, emerging technology research projects, and code compliance studies.
Today we will be highlighting the most significant changes from IECC 2009 to IECC 2018. Then we will be taking a closer look at infiltration.
There are several major changes from IECC 2009 to IECC 2018, which affect both the prescriptive and the performance compliance paths. For projects choosing code compliance through the performance path, the biggest change is that the design building energy costs should not exceed 85% of the standard reference design building. This is a more stringent requirement than IECC 2009, where the cost simply needed to not exceed the baseline. There are also two new sections in IECC 2018. The first new section is Additional Efficiency Packages, which applies only to prescriptive path projects. These projects are now required to comply with at least one of the energy efficiency options under this section. For example, if the reduced lighting power option is chosen, a project will need to reduce its interior lighting power by 10% or more than the base allowance. The other new section in IECC 2018 is Maintenance Information and System Commissioning. This is a new mandatory section that applies to both prescriptive and performance paths and requires buildings to have a detailed mechanical, service water heating, and lighting systems commissioning plan. Having a good design is just the first step to achieving an energy-efficient building, but buildings don't always operate as designed. This is where third-party commissioning comes in. Having a comprehensive commissioning plan helps ensure that the building HVAC and lighting controls are programmed correctly and operate as intended. A commissioning checklist is always handy in the field. Note that mechanical and service water heating systems with capacities less than a certain threshold are exempt from the commissioning requirement. Systems serving individual dwelling units and sleeping units are also not required to complete commissioning. Refer to the code for additional details. Besides the addition of the new sections, the updated code has made the performance requirements more stringent for envelope, mechanical, service water heating, and electrical aspects. Roof and wall insulation now have higher R-value requirements. Window performance thresholds are more rigorous, and there are additional air sealing requirements. HVAC equipment minimum efficiency levels have also gotten more rigid, with additional requirements on the controls. As LED lighting has become more accessible in the past 10 years, the Energy Code has tightened its lighting power density requirements to encourage the use of LED in place of fluorescent and incandescent lighting. Lighting controls are also required in most space types through occupancy, vacancy, and daylighting sensors.
We will not go into detail on all the changes I just mentioned, so make sure to keep an eye out as you go through your first couple projects, as many things have changed.
For the remainder of this video, we will be discussing the specific changes to the IECC 2018 air leakage section of the building envelope requirements.
So, what is air leakage? Air leakage, also referred to as infiltration, is when unconditioned outdoor air enters a building through cracks or openings in the building's envelope. Unintentional air leakage can be caused in many ways. The first way is from wind. Wind creates a positive pressure on the windward-facing walls and negative pressure on the non-windward or leeward-facing walls. This difference in pressure causes air to enter or leave the building through openings in the envelope. The second cause of air leakage is known as the stack effect. Throughout the year, warm air rises upward in a building. When the indoor air at the top of a building is warmer than the outdoor air, it escapes through openings in the building's envelope. This causes the pressure at the base of the building to drop, which in turn draws the cooler outdoor air in through openings in the building's envelope. Stack effect is most apparent in the winter when the temperature difference between the indoor and outdoor air is the greatest. Finally, mechanical equipment such as fans and blowers can generate a pressure difference between the indoor environment and the outdoor environment. If more air is exhausted from a building than is supplied, it generates a net negative pressure. This causes unwanted infiltration through the building envelope. So, why is it important to reduce air leakage? In all the cases of air leakage we discussed, when there's infiltration, conditioned air is also leaving the building. This is called exfiltration. Infiltration and exfiltration act as a double penalty. You lose air that was already conditioned, and you'll have to condition the new air entering the space. This results in an increase to the heating and cooling load. Reducing air leakage will bring this load down, decreasing energy consumption and operating costs. The decrease in heating and cooling load also creates the opportunity to reduce the capacity of the heating and cooling equipment. This allows projects to reduce first cost. In the summer, infiltration brings hot, humid air into the building. When this air hits the cooler indoor surfaces, it creates condensation, which can lead to mold or rot within the building envelope. Reducing air leakage lowers the amount of moisture that enters the building, making for a cleaner indoor environment for all occupants. As the building's envelope gets tighter and the air leakage is reduced, there is an increase in the amount of ventilation air required. This allows for more of the fresh air that occupants breathe to be filtered, decreasing the number of pollutants and pollen within the building envelope. Make sure to follow all mechanical ventilation codes, conduct testing and balancing, and commission controls to maintain proper outdoor air rates. Also consider referencing ASHRAE's ventilation standards 62.1 for commercial buildings and 62.2 for residential buildings.
Now that you understand what air leakage is and the importance of reducing it, I will now go over the code requirements for air leakage, Section C402.5 of IECC 2018. This section is mandatory for all projects, regardless of prescriptive or performance compliance path. There are two different ways to comply with this section. One is the non-testing method, which requires compliance with several items. The other requires blower door testing. Regardless of testing or non-testing method, all projects must comply with a few mandatory items, as shown on the screen here. First of all, dampers should be provided for stairway enclosures, elevator shaft vents, and other outdoor air intakes and exhaust openings integral to the building envelope. Second, cargo door and loading door openings should be equipped with weather seals that restrict infiltration and provide direct contact along the top and sides of vehicles that are parked in the doorway. Last but not least, building entrances should be protected with an enclosed vestibule, with all doors equipped with self-closing devices. One important thing to note here is that the interior and exterior doors should not need to open at the same time to allow for pass-through. When revolving doors are installed at the building entrance, any doors adjacent to the revolving doors should be provided with a vestibule. There are a number of door types that are not required to have a vestibule, such as doors not intended to be used by the public or primarily used to facilitate vehicular movement. Refer to the code for a full list of exceptions. The non-testing method of the air leakage section includes detailed requirements on the air barrier, fenestration assemblies, rooms containing fuel-burning appliances, doors and access openings to shafts, chutes, stairways, and elevator lobbies, as well as recessed lighting. There are a few characteristics of an effective air barrier. The most important aspect is that it needs to be continuous throughout the building thermal envelope and across all joints and assemblies. Connections should be made between foundation and walls and windows or doors, different wall systems, walls and roof, and any surface across construction, control, and expansion joints. It can be located either on the inside or outside of the building envelope, or within the assemblies composing the envelope, or any combination of those scenarios. Try a pen test to confirm your air barrier is continuous. Can you follow the identified air barrier layer throughout the building thermal enclosure without lifting your pen? In addition, care should be taken to make sure joints and seams are sealed, penetrations are caulked, gasketed, or otherwise sealed in a manner that is compatible with the construction materials and location. Sealing materials should be securely installed in or on the joint for its entire length and around the penetration so as not to dislodge or loosen. This strengthens the durability of the air barrier. In the architectural plans, it is very important to call out air sealing details for trades to follow, and to coordinate sealing with the appropriate trades. For example, the plans should clearly note the joints between assemblies and fenestration, duct, plumbing, and conduit penetrations. Make sure it is well communicated to different trades on which party is responsible for sealing which component, as well as the order of the ceiling. Confirm that the air ceiling details in the plans are adequate and constructible. Air barriers need to be strong enough to withstand positive and negative loads due to wind, stack, and mechanical pressures, and durable enough to deal with moisture, temperature, and building movement over the intended lifespan of the enclosure. Here we show an example of a checklist that could be used to confirm that air barrier construction details are in compliance with code. This can be assessed during both plan review and site inspections. In addition to being continuous, air barriers are also required to comply with either the materials approach or the assemblies approach in the code. If complying with the materials approach, the air barrier needs to be of a material that's impermeable to air. Code requires this air leakage rate to be no greater than 0.004 CFM per square foot at 75 pascals under appropriate testing standards. There are 16 materials in the code that meet this requirement. When determining material choices, it is important to ensure compatibility and integration with other building enclosure materials. In construction drawings, specifications should be clear and call out the appropriate testing standards. A checklist may be used to make sure that the install location and type of each of the materials that form the air barrier are included in the construction documents, and that the air barrier materials are found in the materials list in the code, or are shown to meet maximum material leakage rates per the appropriate testing standards. If complying with the assemblies approach, assemblies of materials and components that make up the air barrier are then required to have an average air leakage rate not greater than 0.04 CFM per square foot at 75 pascals under appropriate testing standards. There are 3 assemblies in the code that are deemed to comply. It is important to ensure that the air barrier system is detailed in the construction documents, and specifications are provided to show that the assembly's air leakage is not greater than the maximum threshold. When designing an air barrier, it is very important to consider the building type, expected service life of the building, intended interior conditions, construction type, building height, and building enclosure system type to determine what works best. The key performance of the system is dependent on the proper design and detailing, tested materials that are durable, installation by certified applicators, and proper site inspections and testing for commissioning of system. Fenestration assemblies are also an important piece to consider when designing an effective air barrier. Refer to the code for a table of maximum air leakage rates for different fenestration assembly types. Ensure that the air leakage of all fenestration assemblies are listed in the window schedules in the construction documents, and that they comply with code. For site-built fenestration assemblies, make sure that documentation is included in the specifications that these assemblies are tested and sealed to meet code requirements. Apart from air barrier requirements, there are also a few additional items that projects need to comply with under the non-testing method. When combustion air is applied through openings in an exterior wall to a space containing a fuel burning appliance for space conditioning, projects should follow one of the following options. The first option is to have a space containing the appliance located outside of the building thermal envelope. The second option is to have the space enclosed and isolated from conditioned spaces. When this option is selected, the space must be insulated in accordance with the envelope requirements, where the walls, floors, and ceilings are not less than the basement wall R value requirement. The space should be sealed off from the rest of the conditioned space, and the door into the space should be fully gasketed, and any water lines and ducts in the room should be insulated. The combustion air ducts should be insulated to a minimum of R8, where it passes through conditioned space. For any doors and access openings, from conditioned space to shafts, chutes, stairways, and elevator lobbies, they should be weather stripped and sealed properly. Recessed lighting installed in the building thermal envelope should be IC rated, labeled with code-compliant air leakage, and properly sealed between the housing and interior wall or ceiling covering.
The second way to comply with the air leakage section of IECC 2018 is by completing a blower door test. A blower door is a device that pressurizes or depressurizes a building to determine the leakage characteristics of a building's envelope. A variable speed fan is temporarily mounted in a doorway or other opening to pressurize the building by specified amounts. The flow rate through a calibrated orifice is measured at the pressure differential. The relationship between the flow rate and pressure differential is an indication of shell air tightness. IECC 2018 requires that blower door tests be done according to ASTM E779. The test must show an air leakage rate of 0.4 CFM per square foot or less at 75 Pascal pressure differential. If you choose to comply with IECC 2018 air leakage section by doing blower door testing, there are a few tips to keep in mind. First, commercial blower door testing requires multiple blower doors to complete the test. The building layout needs to be reviewed to determine the quantity and location of fans that will create an equal pressure throughout the building. Also, the building needs to be prepared before testing can be done. A few of these preparations include turning off all mechanical equipment, temporarily sealing all HVAC penetrations, closing mechanical vents, opening all internal doors, and closing all external doors and windows. We recommend that you hire a professional to do the blower door testing. It is complicated and the professional will be familiar with the procedure, standards, and building types to make sure the testing is done efficiently and correctly. It is also important to take all of the advice the testing agency gives you. This will minimize the number of tests that need to be completed. Make sure that you follow any pre-testing checklist that the blower door testing professional provides. If a site is not prepared for a test, the testing will either need to be completed another day or it will fail to meet the IECC 2018 requirements. When air sealing, there are a few key areas to focus on. First is changes in material. This includes spaces where vents or exhaust travel through the building envelope or where envelope construction varies. Second, it is important to pay attention to changes in assembly, such as window-to-wall connections, floor-to-wall connections, or attic-to-wall connections. Finally, even though you are not required to follow all the air sealing sections in IECC 2018, implementing them will help put you on the right track to passing the blower door test.
There are a lot of indoor air quality issues associated with air leakage. Complying with the new energy code helps mitigate these issues. There are 2 ways to meet the new code in terms of infiltration. And remember, whole building blower door testing requires a professional consultant.
By working together, design and construction professionals can make buildings more airtight, energy efficient, and resilient through compliance with the new energy code.
Thanks for watching our video on the latest IECC code update. We hope you learned a little bit more about the code requirements for air leakage.
Keep watching as our colleagues Jennifer Lai and Kevin Frost take a deeper dive into lighting and HVAC controls.